All right, everybody, welcome to the tutorial for Lab 3 for the BYU ME372 class. Feel free to download the lab off of Learning Suite. If you haven't done so already, feel free to pause and do that. But just so you know, we'll be going over how to model this cantilever beam here. And there are only a few small changes from Lab 2 and 1. And so I'm going to go rather quickly through the old stuff that you can review from Lab 2 video. And as I get to the new stuff, I'll slow down and explain it a little better. So I'm just going to get into ANSYS and jump right to it. So same steps for the preprocessor and element type, add, edit, delete, except this time we're going to be using a beam element. So we'll click to node 188. And remember, a beam element models a cross section and pulls that cross section along a line that you draw. And then we're going to skip real constants. We're going to use material properties for this lab, just like before. Material properties, material models, structural, linear, elastic, isotropic. And in the lab, it says 1020 cold drawn steel. That might not be updated in your version of the lab, but we'll be doing 1020 cold drawn steel. So I'm going to use the numbers for that in US units. So 27,000 PSI and 0.29 for Young's modulus. And we're actually going to input a density into ANSYS this time, because when ANSYS knows an exact 3D model, it'll use a density tool to do all of its own weight calculations for you. And it's 0.284 inches per, 284 pounds per inch cubed for that steel. So I'm going to close out that window, and I'll go to the sections. This is the new one. This is new. A section is a cross section that you specify, and ANSYS will extrude that cross section along lines that you draw. So there are a lot of possibilities here. So we're going to go into sections, beam, and common sections. This beam tool's here. ID1 means the first cross section we're identifying, and I'll name it square. And then the subtype drop-down menu is where you choose a common cross section that you want to use, even a smiley face if you want. We're going to use a square one, and we're going to specify the base and the height. In the lab, it says that the cross section is 1 by 1 for the square and 0.9 inch of diameter for the solid tube. So it looks like my window got hidden, so I'll use raise hidden. So, but I believe in ANSYS, the B and the H are actually backwards from what you think, what you think it will be. So the base will actually be kind of look like the height once it's plotted in ANSYS. But anyway, NB is the number of divisions along the base. So how many nodes do you want along the base of your cross section? So I'm just going to put 10 and 10, and you'll see how that is represented later, or what those nodes mean. So if I want to make a second cross section, I'll hit OK, and I'll save it, and I'll open up that menu again by clicking on Common Sections, and this time I'll just type in a 2. So don't miss that. Type in a 2 first, and then you can add a second cross section, and I'll name this one just tube. So we're going to pick a solid tube, and then now we have a new shape and new numbers to specify. So the radius was, the diameter was 0.9, so I'll do, sorry, I did the math in my head. I'll do 0.9 divided by 2 for our radius, because the diameter was 0.9, and then n is the number of divisions on the outside of the circle, so like how many slices of pie you want to divide this circle into, and each slice will be an element. So I want, let's just say 40 nodes around the outside of the circle. And then T is how many rings you want to divide up the circle into, kind of like the rings on a tree if you would cut one open. So I'll put 10, so we'll have 40 slices of pie and 10 different rings. And then it pulls that shape through along the length of the cross section when it breaks everything up into elements. So I'll hit OK, and it saves that one. And that's all I'm going to do with sections. So the next thing here is modeling. We're just going to create key points in ActiveCS. And it's the same thing as before. We can just type in the key points we want, hit apply, and the next key point is at 18 in X. I'll hit apply again, and the next one is 18 times 2. And I'll hit OK to close out the window, and when I hit OK, it closes out the window and applies that number. So there's my 3 key points, and I just want to create, not key points, but lines and a straight line. And so again, with this one, you just click 2 key points, click, draws your lines, hit OK. And meshing, this will be kind of new. So I'll slow down a bit here. Remember, meshing attributes is where you tell ANSYS what you want it to turn these lines into. So I want one line to be a certain cross-section, one line to be another. So I'm going to actually pick specific lines to give attributes to. So I'll do mesh attributes and pick lines. And then I'll click this first line and I'll hit OK. So now I want to apply these attributes to it. One material, no real constants, that's for the truss elements. And we'll do the same element type for both. And then here's where the cross sections come into play. We're going to do the first line I select will be the square cross section, so I'll keep that square, and then I'll hit OK, and it turns that into the square. And then I pick this line on the right, hit OK, and I'll do element section number 2 for a tube. So now ANSYS knows what those two lines are going to be, but it doesn't know how to divide those lines into nodes, so I have to go to size controls. So size controls, manual size, lines, all lines, we're going to divide them up all evenly. If you remember, the edge length is where you specify how wide you want each element to be. So if I put in 1, it'll be 1 inch wide. Or I can do a number of divisions. It'll divide each line into a certain amount of divisions. So I'm just going to put 20. And now, if you remember earlier, for each cross section, we specified an x and a z, we specified 2 dimensions of how it was going to divide up those elements. We specified how many in one direction, how many in another. And now we've given it a 3rd dimension of how to divide up the elements. So when we apply our cross section, it'll have a 3D mesh of elements going through our whole model. So if something's not meshing correctly, you have to think whether or not you've applied specific sizes to your elements in all 3 directions. So 2 directions on your cross section and a 3rd direction when you extrude it along the line. So now we're going to mesh those lines. Same as before, we'll just pick all. And there's our solid blue line that shows that we meshed. But again, if you want to see the shape, you have to go to plot controls, style. So again, plot controls, style, size and shape, and click on the display of element box. Okay, we'll hit OK there. And that's it for meshing. Again, we can click Control and right click to rotate and make sure that our cross section is accurate. It's kind of ugly, so I'm going to turn off those white lines with plot controls, style, edge options, and I'll hit none for the element outline style. I'll turn that to none, and then I'll change this to replot so it actually applies the changes, and I'll hit OK, and then my lines disappear and I can see my model better. So the next thing we want to do is apply the loads. You'll notice in the lab write-up, it says that you want, in the first load case, apply a point load of 1,000 pounds at the end of the beam. In the second case, apply 1,000 pounds as a distributed load. Wrong one. So we'll do a point load the same as before. Loads, define, apply, structural, and force moment. We're going to apply a force. So we'll do that on a key points. We'll click that key point right there at the end, hit OK, and I could specify in the Y direction, I want -1,000. So I'm not going to do that yet. I'll show you how to do distributed load first. But in your lab, it'd be easier to put on the point load and to solve, and then go back and just delete that point load in your session editor or using the define delete structural force on key points. So you can delete it that way and then reapply your distributed load. But for the distributed load, it's a finite element program. It can't apply a nonlinear distributed load. So what we're going to do is apply a force moment on nodes, because if you remember, we broke this whole thing up into 20 nodes per line. So I'm going to actually select this box feature here, and then I will left click and drag a box over it, the whole model, and it'll select all the nodes in the box. So I can put 1,000 pounds divided by the number of nodes on each one of those nodes. So you'll notice the count here is 41 nodes. Might be different for you depending on how you divide it up. But 41 nodes, so I'll hit OK. And then I'm going to apply this force on all of those nodes. So I'll do in Y, and I'll do -1,000 pounds, but this time it's over 41 nodes, so divided by 41. Hit OK, and now all my forces are there. But if you've been paying attention, I haven't locked down the end of the beam that's attached to the wall, so I have to go to define apply structural displacement and on key points. So we want to pick that key point at the end, by the wall, hit OK, and then we want it to be constrained in all degrees of freedom. So we hit all DOF. Now we'll hit OK, and we have our constraint, we have our applied forces, so we're ready to solve. We won't do gravity just because it's such a light beam, it's negligible. So what we're going to do is just run the solver, just like usual, solution solve current LS. We'll hit OK. It'll take a few seconds. Solution's done. We hit close. And remember, if you have an error or your solution box never pops up, check down here and look at this output window. And at the bottom, it'll tell you an error, and it might say something like, check for an insufficiently constrained model. Then you know that you didn't constrain this end down correctly. But anyways, there's some new things to do in the post-processing here. In the lab write-up, it says, turn in plots of the von Mises stresses in the beam for each loading condition, with the value and location of the maximum stress clearly marked for both cases. So what we're going to do is report the von Mises stress for both point load and a distributed load, and then we'll also report the maximum deflection of the beam for both cases. So we'll have 4 plots, one for von Mises stress and one for deflection on the point load, and one for von Mises and one for deflection on the distributed load. And you'll notice it says report the maximum deflection of the beam for both cases and specify the location of this deflection. So we'll go over how to do all of this just now. So I'll start with the von Mises stresses, but you know how to do that already, so we'll do plot results, contour nodal solution, and we'll just go under stress and von Mises stress, and you can hit OK, and it'll plot all the pretty colors for you. So this is what you'll need for the stresses, but for the displacement, it's another nodal solution plot, so we're still doing plot results, contour nodal, except this time we're going to go into this degree of freedom solution menu, and we can plot just the y component of displacement. So now this time the pretty colors represent how far that section of the beam has displaced in y. So notice at the end it's negative 2.88, and so that's the blue, and it matches negative 2.88. For the purpose of this plot, it makes more sense to show it from the side, so that you can see how far you can see the the y plane is I guess parallel to us, and we can see how far it's displaced in y. But what we want to do is call out, report the maximum deflection, and specify the location of this deflection. So what we're going to do for that is use something called the query results tool under post-processing, and we'll click subgrid solution. And it's the same menu as before with the plots, degree of freedom and stress. So this is where you select what you want to call out. And so we're going to use degree of freedom in y. So we want to call out the maximum or minimum displacement in y. So we'll hit OK. And then there's this nice little box that has max and min buttons. But if you remember, min is the most negative according to a computer, and max is the most positive. So when it says maximum deflection, we know we need to click min. But we're going to click this Generate 3D Annotation button. That's going to make our callout look better. So then I'll hit min, and it shows it's going to call it out right there on the right. And then I hit OK. And there we go. It has called out the location of the maximum deflection and labeled it. So that's all we need for that plot, for specifying the location of this deflection. So you'll do that on both the distributed load and the point load. And if you can think back to your other classes, one of those is going to have a greater deflection than the other, and one of those will have a maximum stress in a different place. So for the point load, the maximum stress should be back at the wall, but for the distributed load, it might be in the middle. Actually, I might have reversed that, but one will be at the back of the wall, and one will be actually in the middle of the beam, right at the top of this. And if you could think about your the VQ over IT and equations like that, you can kind of put together why the max stress is on the top of the circular section in the middle, even though the moment arm is so much shorter there. Anyways, something you're going to want to know for printing out good plots and ANSYS is these commands here. If we go to plot controls and then all the way down to best quality image, we can hit create best quality. And we have all these options here. We have resolution options, coarse, normal, fine. We can put a shaded background in there. I'm just going to click no. And then I want to replot. So I'll hit OK. And it'll make when it does this, it'll print out a better looking image, but if you notice my callout here is a little messed